Week 13, part 2. I'd just like to work an example for eyeglasses. We talked about this in our Zoom session, but just to review a little bit, the idea of eyeglasses is for people whose eye can't actually focus on objects at the full range that you'd like. Somebody might be able only to focus on objects that are between 31 and 18 centimeters, either. Um, and this would be a person who is nearsighted. So they can see these near objects, but when things are far away, then they're blurry. Their eye can't accommodate that far. What you normally want is for the far point to be at infinity, and then you end up with a near point different than what it would be here. So we're going to work on that case right here. So if we've got an individual like this would be a myopic person because their far point is not infinity. It should be at infinity. And they're old because there isn't a whole lot of difference between these two. And so they've got a limited accommodation in their eye. So what do? The idea is that you take, when you really do have an object at infinity, the rays from an object at infinity are essentially coming in parallel. And what you have to do is put a lens here so that those rays diverge. It's got to be a negative lens. So they diverge and seem to be coming from a point closer that would be within this range. And for infinity, we would make it be exactly this 31 so that their new far point is in fact infinity. So the way we do that, let me just set up a sort of repeat that chart down here. So their far point is 31 and their near point is 18. So these are the numbers for the eye. And out here, we want reality to be infinity for the far point. And we would like the near point, well, we don't know. I'd like that to be as close as possible, but it won't be. So we'll see what it is. But we first have to figure out what lens to prescribe to put in front of their eye to fix the far point. So let's work part A. The idea is to use this same formula we use for a lot of things. Object plus 1 over S image equals 1 over F. So we want the object to really be at infinity, but for the rays hitting the eye to be coming as if from this point 31 centimeters away so that their eye can focus on it. So the object is really at infinity. That's this term. We want those rays to seem to be coming from a point 31 centimeters from the lens or from the eye. We kind of ignore the distance between the lens and the eye here. 31 centimeters, but it's 31 centimeters on the wrong side of the lens. We're not taking these rays and focusing them to a point out here. We're making them diverge as if from a point over here. That's a negative distance there. And so we put that in as minus 31 centimeters. And that equals 1 over F. And you can solve and figure out what F is. It's immediately obvious because 1 over infinity, that's 0. So we really only have these two, and it's just pretty obvious from that F is minus 31 centimeters. So this is a lens that has a negative focal length. It's a diverging lens with a focal length of minus 31 centimeters. We can work out the power for that. The power would be 1 over 0.31, and that works out to be 3.23 diopters. Diopters are inverse meters. And you have to always be sure and put your number in meters to get the right number in diopters. So this would be an appropriate lens to prescribe, except that, of course, they only come by quarters. So you'd pick 3.25, presumably. That's as finely as they make them. That's great. Now, what is the new near point for the person when they're wearing these glasses? Their near point won't be the same. Just as we've moved the far point out, the near point will also move further away. Where will that be? Same equation again, 1 over SO plus 1 over SI equals 1 over F. This time, we're wondering, where do you really put something so that it seems to be 18 centimeters away? So 1 over SO, that's what we're trying to find, plus 1 over SI. Well, we want it to seem to be at 18, but once again, this is negative. It's gonna be, because this lens is negative, it creates rays that diverge, and the object distance, or the image distance, I should say, is negative. It's on this side of the lens. So that's why that minus sign is there. Now, we're using the lens we just found. We're trying to figure out where the object would be that would seem to be at 18 when it's using this lens. So now we can calculate all of that and see what we get. And you'll find that the object distance is 42.9, or about 43 centimeters. That's kind of far away. That means this person really won't be able to just wear these glasses for everything. They'll have to take them off to read or do something, or get bifocals. So if you were to give them bifocals, in part C, the question is, what lens could you put in the lower part of those glasses for close work that would give them a near point of 25? So for part C, let's try to get a near point of 25. So their normal near point is 18. We want to move it out to 25. And then if they really want to work close, they can always take off the glasses. But for most things, 25 isn't too bad. So what do? What is going to be the lens that we use for this case? So now what we want to do is we want to have an object really be at 25. That's what we want their new near point to be, but it should seem to be at 18. And what lens would that be? So we'll get a focal length from this. Once again, you're going to have an object out here at 25, really 25 away. So that's the regular 25 distance here in front of the lens. But then the image formed by that lens is going to seem to be at 18. And that's where we have this minus sign, because that's an image on the wrong side of the lens. So we still have that minus sign there. You can find the focal length for this, and it turns out to be minus 64 centimeters. That means the power of this lens is, that's just 1 over 0.64, and that power is, and I should keep the minus sign in here, minus 1.55. So here the idea of the prescription is you'd get, in your distance part of the lens, you'd have 3 1/4 diopter, and in the close part of the lens, incidentally, these should all have minus signs on them up here. Absolutely. And down here in the close part, you'd have minus 1.5. Now in part D, the question is, okay, if you've made the near point 25, what's the far point? What's the new far point in that case? Well, using that very lens, then we can do this whole thing again. 1 over SO plus 1 over SI equals 1 over F. We're going to use that lens, so that's 1 over minus 64. That we're keeping. We would like to know where the new far point is. So where do we really put an object so that it seems to be at 31? Where do we really put an object? Well, we don't know what the object distance is. It's what we're trying to find. And this, again, has this minus sign in here. Minus 31 is what the far point is now. What will it be? And if you do this, you get an object distance of 60 centimeters. And that's very good news, because that means when you're in the close vision, you can see all the way out to 60 centimeters. And when you're in the far vision, you can see as close as 43 centimeters, and these two overlap. So this person will be able to see very well with a simple set of bifocals separated by a line. What's more difficult is somebody like me who has, actually my far point is very close to that. It's about 31, at least in one of my eyes. But the near point for that same eye is not 18, it's about 25. So there really isn't much range at all. My eyes don't accommodate much at all. For that reason, if you do the same calculation, you'll find that the new near point in the distance part of my glasses, when I look just there, is greater than a meter. So it clearly can't work as ordinary bifocals. I could be able to see close and far, but very little in between. And so I have progressive bifocals that allow you to adjust kind of everywhere in between. They have all kinds of other terrible disadvantages, but they do allow one to see lots of distances.